Hi, this video is on mass and weight, telling the difference between the two, and relates to Young and Freedman's University Physics, Chapter 4, Section 4, although any physics textbook will somewhere cover this. So the main point of this small section is that mass is not the same as weight. Now, in general, in everyday speech, we treat the two as if they're the same, but really, they're not exactly the same. If we're on the surface of the Earth, there is a direct relationship between the two of them, but if we're in outer space, it's out the window. So basically, mass doesn't change. Weight changes by location. Quick footnote, this is at non-relativistic speeds. That is, mass does change when you approach the speed of light, but that's not important right now. For all intents and purposes, in ordinary life, even in space travel light as we now know it, mass doesn't vary, but weight does. We might say that mass has to do with inertia. This is a nice way to define it, that force equals mass times acceleration, and the way that mass and acceleration works with force is the same no matter where you are in the universe, as long as you're not moving at speeds close to the speed of light. So mass has to do with inertia, the propensity of a body in motion to stay in motion, and a body at rest to stay at rest, Newton's first law. Now weight is the force on a mass. Usually when we talk about weight, we're talking about the force on a mass that's caused by gravity. And so you can see science fiction movies where a rotating thing creates by inertia the kind of verisimilitude of weight, so that you can walk in space, but that's not important right now. When you're talking about being on the Earth, weight is the amount of force on a mass caused by gravity. So we say if F equals ma, then weight equals mass times the gravitational constant, which is 9.8 meters per second squared, or 32 feet per second square if you want to go pounds. But anyway, so weight equals mass times the gravitational constant. You can see that here that mass and weight are not the same, but weight has to do with the force on a mass because of gravity. Okay, I don't know if I've made that very clear, but hopefully by the end of the second slide it will be. Weight varies with location. So you weigh more at sea level than you do in an airplane. It's not a lot. I've never noticed the difference. But when you're 33,000 feet up in the air in an airplane, the force of gravity on you is just less than if you're standing at the Dead Sea in Israel or near Israel. So anyway, weight varies from the top of a mountain to the bottom of a valley, because the gravitational constant is minutely different depending on how far you are from the center of the Earth. So you can see your mass stays the same. Your mass is the same whether you're in an airplane or at the Dead Sea, but your weight will vary just a teeny bit because of the force of gravity. Now, just to give you an example, 1 kilogram is a unit of mass. 1 kilogram on the moon weighs 1.6 newtons. Newton is a quantity of force, rather than the weight of that kilogram on the Earth, which would be 9.8 newtons. So kilogram is a unit of mass, newton is a unit of force. So basically, I would weigh about 6 times less on the moon than I would at the surface of the Earth, because the force of gravity on the moon is about 6 times less on its surface than the force of gravity on the surface of the Earth. So again, weight is a force and is measured in newtons in science class. Kilogram is a mass, and it's what we use also in science class. Now, in everyday language, we talk about pounds in English. That's not actually a unit of mass, it's a unit of weight. The English unit of mass is the slug, believe it or not, which nobody's ever heard of. We don't talk about how many slugs I am. I have a mass of such and such slugs. Anyway, just stick to science. How about that? So, weight is not mass. Mass is the same no matter where you go. Weight changes depending on the force of gravity upon you. That's why you can jump on Mars.